Hello, everybody. So welcome to week 3, lecture 2. This lecture is Analytic Limits, Removable Discontinuities. So this lecture will help you meet the following course learning objectives: SLOA, apply the concept of limits, by evaluating limits using appropriate techniques and properties of limits, and by making appropriate use of available technology, which we will be using a computer today to do some useful things. So this might be kind of a long lecture compared to some of the previous ones, but there's not much we can do about that. Topic's just a little bit longer. So let's go ahead and get started here. So in the previous lecture, you learned how to evaluate limits of polynomials and rational functions, but there's other types of limits that have issues similar to the divide by zero problem you've already looked at. The divide by zero problem is really what we're going to be calling removable discontinuities, although we'll discuss it a little bit more precisely soon. So what are removable discontinuities? So removable discontinuities are x values where the graph has a hole where a single point is missing. Okay, so we've already seen that happen before, right? And I say because it's only a single point, ignore the parentheses, the function could be continuous if the hole were filled in. Now, I say that the hole is at a single point, but you could have like a hole in one place and then in another place you could have another hole. Just because you have 2 or 3, that doesn't mean they're not removable discontinuities. You can have more than one removable discontinuity, but the issue is still the same, that you have a hole where a point is missing. Okay, so don't get hung up on the single point, right? It could be more than one point. Now, the key here is that because it's just a hole in the graph, if the hole were filled in, everything would be fine, right? Like if you have a missing point on the graph, you fill in the missing point, now you have a continuous graph. So you removed the discontinuity, right? If you fill the hole, then it's not a hole anymore. Okay, so that's why we call them removable discontinuities, because it's just a hole that could be filled in. Okay, and we'll look at some pictures of them to see what they look like. So, here's a basic graph that we've seen something very similar to before, a couple of lectures ago. And this is usually what happens when you have a quadratic over a linear function. This one here is x squared minus 5x plus 6 divided by x minus 3. Of course, that does not exist because you cannot plug in a 3, because you'll have a 3 minus 3 in the denominator, which will be 0 divided by 0. And also you'll have a 0 in the numerator, unless I made a mistake there. But I don't think I did. I think it's okay. Okay, and so this graph is not defined, or this function is not defined at 3 because of the divide by 0. And if you look at the graph, you can see that there's just a hole at the point 3, 1. Okay, and so we've done problems just like this already. This is not new. Okay, so this is like a rational function with a divide by 0 issue, and we know how to handle that. But it's not just polynomial over polynomial that we're concerned with today. We're dealing with more complicated things than this. So some of the other things we might be dealing with are like this one. Here we have a graph, and just looking at the picture for the graph, you can see that, you can see that on the picture of the graph here, you have a point at 4, 0.25 is missing from the graph, a missing point. But it's not a straight line this time. If you look at the curve carefully, you can see that it's not a straight line. And if you look at a formula for the function, you'll see that it's a graph of the function square root x minus 2 divided by x minus 4. And if you consider trying to plug in 4 to calculate f of 4, you're going to have the same issue as the previous case, where the denominator here, x minus 4, will become 0, and also the numerator will also be 0 if you plug in a 4. because the square root of 4 is 2 and 2 minus 2 is 0. So it's the same kind of thing, but what makes this one different is obviously the square root of x, right? That's what's different about this problem here. And so I'm going to refer to this as the square root type of problem when I solve problems like this. Okay, so this first one that we looked at, I'll probably call polynomial type. The second one that we're looking at, I'm going to call square root type. And the third type here, I'm going to call fraction type. And because I typed it out here the way you would type it into like a computer and not typeset it pretty, it might be hard to see the function here. But this is a graph of the function. Numerator is 4 over x minus 2. And the denominator is x minus 2. And so this does not exist because if you tried to calculate f of 2, the denominator would be 2 minus 2, which is 0. And the numerator would be 4 over 2, which is 2, minus 2, which is 0. So it's another 0 over 0, right? And I call this the fraction type because 4 over x, that's not the kind of thing that happened in the previous case, right? There was no 4 over x type thing in the previous two examples that we looked at. But on the graph, you can see that there's a hole at 2, right? So it's the same kind of discontinuity as the other ones in the sense that it's just a hole in a graph. Now this graph has other things going on, right? Like it has like a vertical asymptote, but the vertical asymptote is a vertical asymptote. We're not looking at that. We're looking at removable discontinuities, which are just holes. So you see this hole at x equals 2. That's a removable discontinuity. And I'm going to call problems with this type of issue fraction type. And when we see it typeset, it'll make more sense. You'll see a fraction in a fraction. And that's what makes it the fraction type. Okay, so how are we going to go through and we're going to solve these? Well, the first type, we already know how to solve. And I think we'll do an example of that first. But just kind of a overview of this process here. The idea is this, okay? So you have a limit, and the limit is as x approaches a. And f of x happens to have a removable discontinuity at a, right? Just like the polynomial type, the root type, or the fraction type examples that we just looked at, okay? So in that case, what you want to do is you want to remove the discontinuity. Now, we already saw how to do that one time with a polynomial type, okay? Remember, the issue is the divide by 0, and what we needed to do in the previous lecture is we needed to somehow cancel out the divide by 0. Make there no divide by 0, right? Get rid of the divide by 0. And the way we're going to do that is going to be algebra, and each type of problem is going to need slightly different algebra in order to get the job done. And that's why I've divided them up into these types: polynomial type, root type, and fraction type, because the algebra is different in each type. So let's start with the polynomial type, because we've actually already seen this before. So the steps that we used to actually evaluate a limit of this type is as follows. The first thing we did was we factored the numerator, and I say numerator and denominator. You just factor everything, okay? So you just factor everything, and after you factor everything, maybe there are terms that cancel. So you try to cancel any terms that will cancel, and then, assuming that this was a problem that could be done with this technique, then what you're going to do is that after you cancel your terms, there will no longer be a divide by 0. And if there's no longer a divide by 0, then you're going to be able to plug in the x equals a. Okay? And when you do that, you're going to probably get a number. And if you get a number, then that's going to be your answer for the limit. Now, if you still can't plug in x equals a after you cancel everything that cancels, then maybe you did not have a removable discontinuity in the first place. Maybe you're looking at some kind of infinite limit, okay, which we haven't studied yet. So hopefully it shouldn't be happening to you too often. But yeah, so we factor, cancel, and then plug in x equals a. So here's an example. I think this is just the same example from the previous lecture, okay, just to remember how to do this. So we're looking at the limit as x approaches 7 of x squared minus 49 over x minus 7. First thing to do would be to recognize this as the polynomial type, because you see a polynomial in the numerator and you see a polynomial in the denominator, polynomial type. You also see that x is approaching 7, which would make both the denominator and the numerator equal to 0, which tells you that maybe we're looking at a removable discontinuity. And so we'll try our procedure here. So how do we start out our procedure? Our procedure would be to factor the numerator. You would also factor the denominator, but there's nothing to factor. So you factor the numerator, x squared minus 49. You should be able to factor things like that. If you can't, then you might want to go use something like Wolfram Alpha. You can just type factor x squared minus 49 into Wolfram Alpha, and Wolfram Alpha will factor that for you if you need it to, right? X squared minus 49, the result is x minus 7, x plus 7. Okay? So, and again, we have already done this. So you factor that numerator, x squared minus 49, into x minus 7, x plus 7. After you do that, you look for terms to cancel. We can cancel the x minus 7 with the x minus 7. Oops. So you cross those off. You're left with limit x goes to 7 of x plus 7. Nothing is stopping you from plugging in the 7 anymore. So you put in x equals 7 to get 7 plus 7, which is 14, and that's your limit. So the limit as x approaches 7 of x squared minus 49 over x minus 7 is 14. Okay, and that's the polynomial type. So we've seen that before. Now, we want to look at the root type. Now, the root type is very similar, to be honest, but there's a thing you have to understand before you can do the root type problems. And the thing you have to understand is what are conjugates in math. And the word conjugate in math gets used a lot. Not a lot, but it gets used in a few different places. And it usually means the same thing. But, each time you see it, it might be a little bit different depending on the discipline of math you're dealing with. At the end of the day, any terms a minus b and a plus b are conjugates. And so the difference between a minus b and a plus b, of course, is that one has a minus sign and one has a plus sign. That's what makes them conjugates, okay? And what's special about conjugates is that when you multiply them, it cancels out a certain way. So whenever you do a minus b times a plus b, the result is a squared minus b squared. Okay, so let's stop here for a second and go over to Wolfram Alpha so I can show you something. Right, if I go a minus b, I'll use lowercase, a plus b. Right, if you have a minus b, a plus b, and you multiplied it out, you would have to do foiling, right? So like first terms, a, and then you would have the outer terms, which would be a and negative b, I guess. Actually, no, a and b. Then you have the inner terms, which would be the negative b and the a, so minus b and a. And then you multiply the last terms, which are negative b and positive b, so minus bb. So that's what happens when you FOIL this. And if you actually write out what that would be, a times a is a squared. In the middle, you have plus ab minus ba, but those are the same. So the middle terms cancel. And then you have minus bb, which is b squared. Okay, so that always happens. That always happens. And that's very useful. The fact that the result, a squared minus b squared, is very helpful, because what happens when you square a square root, right? Think about it. If ever you have like square root 3, right, for example, if you were to take that and square it, of course, square root 3 squared is going to be 3, right? The square root and the square cancel out. And that's what we want. Because if we do something like this, x minus, let's say, 5, x plus 5, something like that, we know that because of the property of conjugates, the result here would be x squared minus 5 squared, right? That's the whole point of conjugates, is that's how it works, which would be, of course, x squared minus 25 when you actually work that out. But what happens if you throw a square root in there? What happens if you put the 5 in a square root? Right? What will happen there? Well, in that case, you would have x squared minus, instead of 5 squared, it would be square root of 5 squared, which would simply be x squared minus 5. Do you see how if you multiply conjugates, any square roots just sort of magically disappear in the answer because you're going to be squaring them? So if I do this, one last one here, square root x, let's say minus 4, square root x plus 4. I don't know why I spaced that all so weird. If you do this, square root x minus 4 times square root x plus 4, you're going to get square root x squared minus 4 squared. So how does that look? Well, the square root of x squared is just x. And the 4 squared is just 16. Okay, so that's how conjugates work. Now, of course, if you're having trouble dealing with conjugates, you can use Wolfram Alpha to help. So like, I think we have an example here. Like on this problem right here, it says, this is nice for square roots, this property, right? Consider square root x plus 2 times square root x minus 2, right? If you multiply them out, which I'll just do here, square root x minus 2, square root x plus 2, if you multiply those out on Wolfram Alpha, here they are, and you scroll down a little bit, you'll see expanded form, just x minus 4, because it's square root of x squared, which is x, minus 2 squared, which is 4. Okay, so this property of conjugates you have to be familiar with in order to do these problems. So multiplying conjugates makes your square roots disappear, basically. Okay, and that's what you need to understand before we talk about the method for solving problems with these conjugates, or sorry, with the root type problems using conjugates. So here is our procedure for doing these limits involving root types. Okay, so what we're going to do, you're starting out with a limit that's a root type. What you're going to do is you're going to figure out what the conjugate is. And then you're going to multiply the top and the bottom of your function by the conjugate. So each problem is going to have a different conjugate. You need to be able to tell what it is. remember that a conjugate is just take whatever the sign is and reverse it, right? A minus b and a plus b, those are conjugates. So you're just going to be changing a sign to make a conjugate. So you multiply the top and the bottom of your function by the conjugate. Then you multiply everything out. After you multiply everything out, you're not going to have any square roots left. Or at least you're going to get rid of the one that you wanted to get rid of. So you multiply everything out, you simplify. You cancel out any terms that cancel. That's the same as the polynomial type. And at a certain point, you're going to be able to plug in x equals a, just like the polynomial type. The only difference is you had to use this conjugate in order to get there. So here's an example. Limit as x approaches 49 of square root x minus 7 divided by x minus 49. Just quickly, you can verify that if you try to plug in 49 here, the denominator will be 49 minus 49, which is 0. The numerator is square root 49, which is 7. 7 minus 7 is 0, so the top is 0 again. So just like before, you're going to end up with 0 over 0 when you try to do this one. So that's what makes it root type and maybe removable. Let's find out. Okay, so there's a lot on the page here. So the main thing to look at first is the numerator was square root x minus 7, right? Square root x minus 7. So the conjugate is square root x plus 7, right? If it's a minus here, your conjugate has a plus. So you're going to multiply the top and the bottom by the conjugate. So this top line is what we're starting with. The conjugate is square root x plus 7. So you multiply your original thing by square root x plus 7 over square root x plus 7. That's what we call multiplying by the conjugate usually. When you multiply by the conjugate here, you can take both of these terms, write them all in one fraction. So in the numerator, you've got square root x minus 7, square root x plus 7. In the denominator, you have the original denominator, x minus 49, and the new conjugate, square root x plus 7. Okay. Now, at that point, you need to just start working things out. Okay. So in the numerator here, you actually need to do that square root x minus 7, square root x plus 7 conjugate thing where you work out what that will be. And, feel free to use a computer to do that if you need to. But what happens is you square the square root x, and going down 2 lines, you're going to end up with x. And you square the 7, and you get 49, and then a minus sign between them. So x minus 49. So that's what the numerator will be, x minus 49. Now, in the denominator, I'm going to tell you, in the original problem, the issue was the numerator, right? The square root was in the numerator. The denominator had no issue other than the divide by 0, but there were no square roots to worry about. And the thing is that on this line right here, the top needs to be multiplied out because it's conjugates, and you need to simplify that. The bottom are not conjugates, and there's actually no reason to multiply that out. So you'll notice that on the second line, I have x minus 49 square root x plus 7. And then on the next line, I have the same thing, x minus 49 square root x plus 7. And on the next line, I still didn't do anything, right? I just left it, x minus 49 square root x plus 7. The reason I never touched the denominator there is I know that eventually I'm going to be trying to cancel some stuff out. I don't want to multiply that out. I only multiply out the numerator because I'm trying to get rid of a square root. Okay, so yeah. So you multiply out that numerator, you leave the denominator alone, and you eventually end up down here. So at this point, you look at it and you see that you have x minus 49 on top, and then on the bottom, you have x minus 49 again, and then also you have the square root x plus 7 that came from the conjugate. But what we're trying to do is cancel anything that cancels. So we're going to cancel the x minus 49 with the other x minus 49, cross out, and what you're going to be left with is 1 over square root x plus 7. Okay, and at this point right here, where you've done that canceling, you've gotten rid of the divide by 0, right? If you look, there's not even any minus signs left. So when you plug in the x equals 49 now, there's not going to be a divide by 0. As soon as you reach that point where you're not going to have a divide by 0, you go ahead and you just plug in the x equals a. So in this case, you just plug in the 49 right there for the x. You end up with 1 over square root 49 plus 7, or when simplified, 1 divided by 14. And so 1 over 14 is the limit as x approaches 49 of this function, square root x minus 7 over x minus 49. Okay, so the key there is knowing that the conjugate is going to do what you want it to do and allow this simplification to happen. Okay, so you have to remember this is how you deal with the root type. You multiply by the conjugate top and bottom. Okay, so that's it for the root type. So now let's look at the fraction type problems. Now, I've got one here that's typeset a little bit nicer than the when it's typed out and not typeset. So look at this. So this example here, you can see 4 divided by 3x minus 2/3 in the numerator, and then all of that over x minus 2. And hopefully you can see why I call these fraction type. It's because you have a fraction overall, but in your fraction, you have more fractions, right? So it's fractions in your fractions. Technically, those are called compound fractions. So compound fractions are the issue here. Okay, and really there's not any really super fancy algebra here. It's just that what you want to do is you do not want to have compound fractions. So we need to figure out how to get rid of the compound fraction. And there's a million ways to do it, by the way. But this is the way that I advocate because it involves what I think to be the least amount of thinking, and thinking's hard. Okay, so the way you're going to deal, or I'm going to suggest that you deal with common denominators here, or the way I suggest you deal with compound fractions is by finding the common denominator. So you look at the fractions in your compound fraction. In this case, you have 4 over 3x and you have 2 over 3. And you say, well, what's the common denominator there? And the common denominator is 3x, right? 3x and 3, the common denominator is 3x. And then rather than doing something like getting a common denominator and add, which is a possibility for how to proceed here, I'm going to suggest that you don't do that. I'm going to suggest that what you do is figure out the common denominator, which I did, 3x, and then I'm going to take that 3x and every term in the entire problem, top and bottom, I'm going to multiply by 3x. Okay, I'm going to multiply that common denominator everywhere. So if you look at this line, you see I threw a 3x, a 3x, a 3x, and a 3x on everything. Okay, and the point of doing that is that if you do some canceling now after you put that 3x on everything, what will happen is you'll have, like on this first fraction, you have 4 over 3x times 3x. The 3x's cancel. And your result at the bottom is going to be just a 4. Your second term here, 2 over 3 times 3x, well, the 3's cancel. So you'll be left with the 2 and also with an x. In the denominator, there were no fractions, So you just have x times 3x, and you have 2 times 3x, which you can multiply out if you want to, or not. The key here is that when you do the step of multiplying everything by the common denominator, is that you'll notice after you do that and do a little bit of canceling, you end up with a result like this one, 4 minus 2x on top, 3x times x minus 2 on the bottom. And the key here is you'll notice that this is no longer a compound fraction. And if it's no longer a compound fraction, then the appropriate way to deal with this will be with the same thing that we do for polynomial types, because it is a polynomial type now, right? So the top here is a compound fraction or fraction type problem, and on the bottom you have a polynomial type problem. So that's what you do for the fraction type, is get rid of the compound fractions, and this is my suggested method. Find the common denominator and then multiply every term in your fraction by that common denominator. Okay, so that's just a hint, I guess. One thing I will show you is, of course, you can always use Wolfram Alpha to help here. So like if I go here and I do like 4 over 3x minus 2/3, that's the numerator, and then divided by, I already forgot the denominator, x minus 2, like that. If you just type in something like this and hit enter into Wolfram Alpha, right, there's the compound fraction, and I bet if we scroll down, it will simplify it. Alternate form, negative 2 over 3x. And if you look here, alternate form, well, it should have been negative 2 over 3x, but I made a mistake here. Actually, I made a small mistake here, because if you look, this is 2 minus x, and this is x minus 2. So they're not actually equal, but I canceled them out anyway. I should have, in order to cancel them, I should have canceled them and had an extra minus sign. So there's a typo here. This should be minus 2 over 3x. But you saw that how I got that was just by typing this into Wolfram Alpha. So you can do the algebra yourself, but you can check your answer just by typing it into Wolfram. All right, so here's an example. So let's say we're going to do this problem right here. It's similar to the previous one, but it is different. Right? So we're evaluating limit as x approaches 3 of 4 over x minus 4 over 3, and all of that divided by x minus 3. If you try to plug in x equals 3, you'll see that you end up with 4/3 minus 4/3 on top, which is 0, and 3 minus 3 on bottom, which is also 0. So this is the same issue as before. It's a 0 over 0, and maybe we can fix it with algebra. So let's try. So what's your common denominator, right? You see the 4 over x and the 4 over 3, and your common denominator is 3x. That's the same as on the previous page, but this is a different problem. So what are we going to do with that? Sorry, okay. So you find the common denominator, it's 3x. You take that 3x and you multiply every term by 3x. So you'll see on the second line here, I've multiplied every term by 3x. There's 4 of them. So everything gets a 3x, 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 3x. Okay. After you do that, you do some canceling. You'll notice that your first term here on the numerator is 4 over x times 3x. The x's cancel. Leaves you with 4 times 3. Your second term in the numerator is 4 over 3 times 3x. The 3's cancel. That leaves you with a 4 and an x. Okay, so after you do that canceling, your numerator is 4 times 3 minus 4 times x. So that's what I have here, 4 times 3 minus 4 times x. In the denominator, It doesn't really matter if you multiply it out or not. In this case, I did. So I multiplied 3x times x, and I multiplied 3x by 3, and I got a denominator of 3x squared minus 9x. So I finished multiplying this out. I multiplied the 4 and the 3 and the 4 and the x, and I've got the limit as x approaches 3 of 12 minus 4x over 3x squared minus 9x. Now, this is polynomial type now. That's where you would go back to the polynomial type problems and realize that what you need to do is factor the top and the bottom and cancel, right? So this is polynomial type. So you still have to factor and you still have to cancel. Can't forget about that stuff from the earlier problems. Now, if you scroll down here a little bit, you'll see that I've got negative 4 over 3x is where I end up. And just to show you, if you go back to the original, if we look at Wolfram Alpha here, 4 over x minus 4 over 3, that's the numerator, over, was it x minus 3? Yeah. So if you type this into Wolfram Alpha, it will do all of the simplifying and tell you that the alternate form here is 4 minus 3x, as long as x is not 3, because remember, you cannot plug 3 into the original because of the divide by 0. So negative 4 over 3x. And if you look at what I've got, my eventual answer here is negative 4 over 3x once I do all my canceling. So you can get, first line to second to last line just on Wolfram Alpha. Have them do your algebra. But backing it up to where we left off, we were at 12 minus 4x over 3x squared minus 9x, polynomial type. So you factor the numerator, you factor out a 4. So you have 4, 3 minus x. In the denominator, you can factor out a 3x, x minus 3. Notice that you're kind of going backwards there. Like we almost had that when we started the problem almost. That happens sometimes. Sometimes you multiply stuff out and then you have to factor. Just how it is. So you factor out a 3x, x minus 3. You need to cancel here. But be careful. When you have 3 minus x and x minus 3, those do not cancel directly. What you have to do is take the 3 minus x, flip it around to x minus 3, but take out a minus sign. So you'll notice from this line here to this line here, I say that 3 minus x is negative x minus 3. So you do that first, and then you cancel the x minus 3 with an x minus 3 because they actually do match now. And that's where this extra minus sign comes from. Okay. In any case, once you do that canceling and you're at the point where you have negative 4 over 3x, nothing is stopping you from plugging in x equals 3 now, right? As soon as you do this canceling, you're able to plug in your x equals a because there's no divide by 0 issue. That's always the goal, remember, to plug in the x equals a once you deal with the divide by 0. So in this case, you plug in the 3 and you get negative 4 over 3 times 3, or negative 4 over 9. Okay, and that's how you deal with the fraction type. One way you can deal with the fraction type. So hopefully you've seen that you can do all this algebra by hand. You can also use a computer where if you just type in, don't worry about the limit, just type in the stuff without the limit and into Wolfram Alpha, and it will do the algebra to simplify it for you. And if you want Wolfram Alpha to factor for you, you have to say factor and then tell it what to factor. Okay, so I think that's it. So polynomial type, root type, fraction type. These limits are very important, and you'll need to practice this stuff before you're super familiar with it. But we're going to be doing it in multiple sections in the textbook. So get started on it now. Come to office hours if you need help. So thanks for watching the lecture, and I will talk to you guys later.